Hello everyone. The title of this presentation is Amalgamating different JIT compilations in a meta-tracing JIT compiler framework. This means the hybrid of different JIT compilations. In what sense our approach is hybrid? The answer is that it is going to support two major compilation strategies in modern virtual machines, which are trace-based compilation and method-based compilation. The motivation for realizing hybrid compilation is faster execution, since the suitable strategy depends on the structure of a target program. Please look at the figure on the left. This program, nest_fun, has nested function calls, and the function fib has a control flow which has branches occurring with equal possibility. Tracing JIT prefers programs which have many dynamic branching and more in-depth function calls like nest_fun. Meanwhile, method JIT works well on average and better for programs which have no biased and frequently executed areas like fib. Therefore, for faster execution, we presume that applying different strategies for defined program parts should be essential. And we notify you that our experiments showed some programs actually run faster by the hybrid compilation. Next, we briefly introduce a technology called MetaJIT Compiler Framework we now focus on. MetaJIT Compiler Framework generates a virtual machine with a JIT compiler from an interpreter. There are two state-of-the-art frameworks. The one is RPython, generating a tracing JIT compiler, and the other is TruffleGraph, generating a method JIT compiler. They can generate fast VMs like PyPy, TruffleRuby, and GraalJS, but current frameworks support only a single strategy, so what's our idea with this situation? Our idea is mixing two strategies in a single MetaJIT compiler framework and compiling different parts of one program in different ways. We choose a meta-tracing JIT compiler as a basis since trace-based compilation is simpler than method-based compilation for proof of concept. We will explain the prototype implementation backend later. To support the two strategies in a single framework, we create a method-based compilation by extending a meta-tracing JIT compiler framework. We call it method JIT by tracing here. Next is for runtime. We call it stack hybridization. Stack hybridization is an interpreter designed to interact with machine code derived from different strategies with each other. In the next sections, we explain the details of method JIT by tracing and stack hybridization. First, we explain the mechanism of method JIT by tracing. The idea is customizing the following meta-tracing JIT compilations features: trace entry and exit points, conditional branches, function calls, and loops. Next, we show how method JIT by tracing works by using an example. The left-hand side is the control flow of an example program, and resulting traces will show up in the right-hand side. This represents the example method. C is a loop header and G is loop edge. This function G is called in this example method. The tracer starts to trace at the beginning of the method. When it encounters the loop header C, it starts a new trace here. When tracing a conditional branch, it saves its state here and continues to trace one branch. When tracing the back edge to C, it leaves jump instruction to C and continues to trace. When reaches to return, if there is an already saved state, it backtracks to that point. It restores the state and restarts to trace the other branch. When tracing a function call, it doesn't follow the call and leaves called instruction to G. When reaches a return, and if there are no stored states, then it finishes tracing. Finally, the tracer generates the traces shown on the right-hand side. Next, we are going to introduce stack hybridization. Before showing the details, we explain why stack hybridization is needed. If machine code generated from different strategies call with each other, the runtime cannot go back to a correct place. We call it combination problem here. For example, we consider this case. Trace compiled function f calls method compiled function g. Calling g from f is successful, but when returning to f from g, it can't go back to the right place. It is because the management of the return address is different between tracing JIT and method JIT. This problem boils down to the difference in the interpreter design between the two. In the next slide, we are going to look into the two interpreter definitions. Two strategies prefer and require different stack styles. There are two stack styles. One is user stack style, and the other is host stack style. User stack is an R-edited structure made by a language developer, and host stack is a host language's system stack. The left-hand side and the right-hand side show examples of user stack style and host stack style. In the user stack style, the return address is managed by user stack in call and return definitions. As shown in blue color lines of code, the return address is managed by user stack. Tracing JIT prefers user stack style since it can compile recursive calls into loops. On the other hand, in host stack style, the return address is managed by host stack. In green color lines of code, the interpreter is recursively called in call definition, and return value is just returned in return definition. So, the return address is controlled by a host language. Method JIT requires host stack style since it needs to leave call instruction as explained in the section of method JIT byte tracing. To solve the combination problem, we propose stack hybridization. Stack hybridization uses both user and host stack styles and puts a flag in the user stack to tell the active stack. HS means host stack and US means user stack. The left-hand side and right-hand side show the definitions of call and return in stack hybridization, respectively. In call, first, a language developer needs to write a pseudo function in MJ. This pseudo function changes JIT context by a given call address. Second, a developer needs to push HS or US flags at the top of branches depending on the JIT context. The developer puts the flag HS at the then branch and puts the flag US at the else branch. In the definition of let, first, it needs to check the push flag by using if then else syntax, and the developer writes the definition of let separately corresponding to the JIT context. In the then branch, for instance, the developer writes the definition of let under tracing JIT context. Next, we will explain how stack hybridization works by using compiled code. Please look at these source codes. Some fib is an example program, some is compiled by tracing JIT, and fib is compiled by method JIT. We consider that the controller enters the native code of SAM. After executing the jump instruction, it goes to the native code of fib. Fib has recursive calls. When it is in the base case, the controller goes back to this point after this recursive call is executed. And the push flag is equal to HS, so the controller goes to this point after the read instruction is executed. Just before returning back to SAM, this comparing instruction turns false since the last flag in the user stack is US, so the controller goes to this section. How do we let the controller to go back to SAM? The answer is using guard failure. Through the interpreter, by using the guard failure, the controller can successfully go back to SAM. Like this, we can successfully connect machine code generated from different strategies by using stack hybridization. Before showing the result of evaluation and experiment, we introduce a proof of concept implementation Backcamo. Backcamo is an RPython-like trace-based MetaJIT compiler framework. It is drastically simplified from RPython and re-implemented in MinCamo and OCaml. MinCamo is a small subset of OCaml, and the compiler generates as fast machine code as GCC or OCaml opt. Backcamo is still prototype, so we have following limitations. We implemented only basic optimizations like constant folding, dead code elimination, and defuse analysis. And our method JIT is more naive than other state-of-the-arts. For example, it doesn't perform method inlining. Some of you may wonder about the quality of our compilers. When we compared our compilers against the interpreter and the native code compiler, the speed was about 19 times faster and 3 times slower on average, so we could conclude that our framework has already achieved some level of quality yet has room for improvement. This figure shows the result of the evaluation comparing standalone JIT strategies with interpreter execution. From this result, we confirm that tracing JIT is suitable for straight-line control flow, and method JIT is better for complex control flow. The height of the bars are speed-ups from the interpreter execution, so higher is better. These 5 programs have complex control flow, and other programs have straight-line control flow. In programs with straight-line control flow, tracing JIT is faster than method JIT. In 5 programs with complex control flow, on the other hand, method JIT is faster than tracing JIT, and tracing JIT is much slower because of the path divergence problem. This is the result of hybrid JIT synthetic experiment. From this experiment, we report that there are programs that can be run faster by the hybrid compilation. As candidates, we chose SAM, fib, and TAC in according to the result of last evaluation. Since fib and TAC are suitable for method JIT, and SAM is suitable for tracing JIT, we synthesize them to create SAM fib, SAM TAC, fib SAM, and TAC SAM, and apply tracing JIT for SAM and method JIT for fib and TAC, like the program on the left-hand side. In SAM TAC and SAM fib, hybrid JIT is about 20 times faster than tracing JIT, and from 1.02 to 1.03 times faster than method JIT. Tracing JIT is much slower due to the path divergence problem, and method JIT is a little bit slower due to the cost of method calls. In fib SAM and TAC SAM, hybrid JIT is from 1.01 to 1.60 times faster than tracing JIT, and from 1.11 to 2.18 times faster than method JIT. Tracing JIT is slower, but not much slower than SAM TAC and SAM fib. It is because tracing JIT could generate longer traces than them, and method JIT is slower due to the same reason in SAM fib and SAM TAC. We summarize this presentation here. We propose the meta-hybrid JIT compiler framework and the prototype implementation Backcamo. We propose method JIT by tracing, which mixed trace and method-based compilations by extending a meta-tracing JIT compiler framework. To interact with machine code generated from different strategies, we propose the dynamic stack switching mechanism called stack hybridization. In the current implementation, we manually select a compilation strategy, so we need to investigate a mechanism to dynamically select a suitable strategy. And then, the current implementation of stack hybridization requires writing pseudocode and flag handlers, so we should develop more fluent API definition for user convenience. Finally, in the future, we need to realize our hybrid compilation on RPython or TruffleGral. Backcamo is a proof of concept, so we need to realize our idea at the production level to validate our assumptions work in real-world programs. Thank you so much.